Lecture 31, Brain-to-Brain Communication Interfaces. Let us begin in 2013, in a lab at Harvard. A human volunteer sits with an EEG cap, staring at a flickering pattern on a screen. Across the room, a rat dozes with a device affixed to its skull. The human concentrates, imagines moving their hand, and, a moment later, the rat's tail twitches. What connected the two was not sight or sound, not language or gesture, but a direct brain-to-brain interface. When the human's EEG signal crossed a threshold, in this case, detecting a specific brainwave elicited by the flashing light, a computer triggered a focused ultrasound pulse into the rat's motor cortex. The ultrasound stimulation activated the rat's brain non-invasively with pinpoint precision, causing its tail to flick. Simple. Primitive. But undeniable. One brain influenced another, directly. It was as if a thought in one head had jumped species and made muscle move in another. What had once been the stuff of telepathy and science fiction was now an experimental reality on the lab bench. This demonstration, the human-to-rat, mind control, was a prototype, not a product. Yet it cracked open a door that had firmly belonged to fantasy. In that moment, the realm of possible communication expanded to include a new and astonishing conduit, brain-to-brain transmission. Since then, researchers have tiptoed and occasionally sprinted through that door. Brain-to-brain interfaces, BBIs, have moved from speculation to active exploration. These are systems in which information extracted from one brain is translated into stimuli that modulate activity in another brain. The applications are still embryonic, the signals rudimentary, but the implications are vast. We are learning, for the first time, how to network minds. To understand how a BBI works, consider the two technological halves it must unite: a brain-computer interface, BCI, and a computer-brain interface, CBI. A BCI reads neural signals from brain A, intention, emotion, imagery, and converts them into digital data. A CBI takes digital input, text, sound, code, and uses it to stimulate brain B. A brain-to-brain interface is simply the marriage of the two: record from brain A, digitize and transmit, then stimulate brain B in a way that conveys meaningful information. In essence, we're hooking up one brain's output to another brain's input. If my brain can talk to a computer, and a computer can talk to your brain, then my brain can, in principle, talk to your brain. The simplest BBIs operate on extremely low bandwidth, just a trickle of information. Think back to the Harvard example: a single binary signal, one bit on, off, triggered a preset action, tail twitch. Even that one-bit transmission required careful calibration. The human's EEG pattern needed to reliably indicate a specific cognitive event, imagining movement, detected via a steady-state visual evoked potential in this case. The rat's stimulation had to hit the right spot in motor cortex to produce a visible twitch. The timing had to be tight and the triggers precise. In effect, the entire loop had to be tuned just right. Mind A generates a signal, computer detects and relays it, mind B receives a stimulus, muscle B moves. One bit across two brains, with an internet cable in between. It wasn't exactly a conversation, but it was a proof of concept that bypassing the usual sensory channels was possible. Since that pioneering study, BBIs have grown a bit more sophisticated. In 2013 and 2014, Miguel Nicolalis's group at Duke University demonstrated a series of brain-to-brain interfaces in rats that truly pushed the envelope. In one experiment, an encoder rat learned to press one of two levers when it felt a particular texture or saw a specific light. Its brain activity patterns from its motor cortex was recorded in real time and transmitted via intracortical microstimulation into a decoder rat's brain. Remarkably, the second rat, which hadn't felt the texture or seen the light itself, responded correctly to the received brain signal significantly above chance. In essence, the second rat's decisions were being guided by information directly injected from the first rat's cortex. Nicole Lees and colleagues even linked rats on different continents, one in North Carolina and one in Brazil, connected by the internet. Despite thousands of miles of separation, and the noisy transmission that distance can introduce, the neural link still worked. The decoder rat pressed the correct lever 70% of the time based solely on the brain cue from its distant partner. Even more astonishing, the communication became two-way. When the decoder rat failed to press correctly, the encoder rat didn't get its reward. In response, it appeared to adjust its behavior, essentially teaching its partner by refining the sent signal. This hinted at a feedback loop between the two animals, a primitive dialogue of brains. In Nicolelis's words, they had created a rudimentary, organic computer, a network of animal brains solving tasks together. Brain-to-brain communication was not only real, it could be reciprocal and cooperative. By 2015, the same lab extended the concept to what they dubbed a brain-it, not just a pair, but a network of brains. In one setup, 3 or 4 rats were interconnected, each receiving partial information and needing to combine it to solve a problem. Think of it like a neural jigsaw. Each rat had a piece of the puzzle, say, a fragment of a pattern or a bit of a sequence, and only by pooling their brain activity could the full answer be derived. The rats, effectively, performed a computation together. The results were crude. These brainets weren't outperforming silicon computers, but they showed improved performance through cooperation, as if the group of brains was averaging out individual errors. In another striking demonstration, a trio of monkeys was wired to collectively control a virtual arm in 3D space. Each monkey's brain controlled certain dimensions of movement, and only by working in unison could they reach the target. The monkeys, without any verbal communication, had to mentally synchronize to earn their juice reward. Their combined brain power moved the arm more accurately together than any one monkey could alone. These experiments, in rodents and primates, painted a provocative picture. When brains are networked, their collective can accomplish things that individual brains might not. In some tasks, 2, or 3, or 4 heads are truly better than one. Humans, too, have entered the BBI arena, albeit at low bandwidth and with much caution. The first landmark was achieved in August 2013 by researchers at the University of Washington, who demonstrated a human-to-human brain interface. One person, the sender, wearing an EEG cap, played a simple video game that involved firing a cannon at a target. Instead of actually pressing the fire button, he merely imagined moving his hand. This EEG-detected intention was sent across campus via the internet to a second person, the receiver, who wore a transcranial magnetic stimulation (TMS) coil over the part of his brain controlling his right hand. When the signal arrived, the TMS device activated, inducing an involuntary twitch in the receiver's finger enough to hit the fire key. The two participants couldn't see or hear each other. The only link was the signal moving from one brain, through a computer, into the other brain. Rajesh Rao, the sender, described the eerie thrill of watching his intention trigger someone else's body. It was both exciting and eerie to watch an imagined action from my brain get translated into actual action by another brain, he said. Andrea Stocco, the involuntary trigger man, likened his finger's sudden jerk to a nervous tick. His hand moved with no conscious will of his own. This was the first direct human brain-to-brain interface validated by peer review, a Vulcan mind meld, in nascent form. Not long after, in 2014, an international team went a step further. They transmitted an actual word from one person's mind to another's using a BBI. In this study, one participant thought of a simple greeting, "Hola," and this word was encoded in binary form, as a series of ones and zeros, by a computer interpreting the sender's EEG signals. Across the globe, a second person's brain received this series of bits via TMS pulses to their visual cortex, which produced patterns of light flashes, phosphons, in their vision. By consciously decoding the sequence of flashes, the receiver could spell out the transmitted word, "Hola," without ever hearing the word spoken or seeing it written. In essence, the sender thought "Ola" and the receiver saw "Ola" in their mind's eye. The process was slow and error-prone, like a very clunky Morse code between brains, but it worked. Around the same time, groups in Europe used similar EEG TMS setups to send messages like "ciao" and "hello" between people in different countries. This was still far from anything like open-ended conversation. We're talking about a few bits per minute, but it was a hint that beyond simple motor commands, even abstract symbols, letters, words, could be conveyed brain to brain under the right circumstances. It wasn't telepathy in the mystical sense. The sender couldn't plant a complex thought or image in the other's head. But the door to semantic communication, to sharing meaning, was opening ever so slightly. All of these demonstrations, disparate in technique and ambition, share a basic scaffolding, a sender, a receiver, and a channel between them. The sender's brain activity is captured and encoded. The signal, usually digital, travels across the channel, wired, wireless, over the internet. The receiver's brain is then stimulated in a way that hopefully conveys the encoded information. This scaffold can take many forms. Some BBIs are entirely non-invasive, a sender wearing an EEG cap and a receiver under a TMS coil, with nothing penetrating the skull on either end. Others are hybrid, perhaps a person with an implanted BCI sends signals to someone receiving via a less invasive method, or vice versa, as in the human to rat example, non-invasive EEG on the human, but focused ultrasound stimulation to the rat's brain. And in animals, researchers often use fully invasive setups on both ends, implanting electrode arrays in all the brains involved for maximum signal clarity. The choice of modality, non-invasive versus invasive, electrical versus ultrasound versus optical, etc., affects everything: how much information can be sent, how fast it moves, what kind of mental states can be transmitted, and how feasible the system might be outside the lab. In short, each BBI is a chain only as strong as its weakest link, be it the recording, the decoding, the transmission, or the stimulation. To appreciate the challenges and opportunities, we need to examine each link in this chain. On the sending side, brain A, the first question is how to capture the sender's neural signals. Most human BBIs to date rely on EEG for this, and with good reason. EEG is non-invasive, just electrodes on the scalp, safe, relatively affordable, and offers millisecond level temporal resolution. It's quite good at detecting large-scale, synchronous brain patterns, the collective firing of millions of neurons that produce telltale waves. For example, an EEG can pick up the P300 signal, a spike in voltage about 300 milliseconds after a rare or significant stimulus, often used to signify recognition or a conscious aha, or mu rhythms that decrease when you imagine moving, reflecting motor cortex idling rhythms, or steady-state visual evoked potentials, SSVEPs, induced by looking at a flashing light at a particular frequency. Indeed, many BBI demonstrations piggyback on such robust EEG features. The Harvard setup used a flashing light to evoke an SSVEP. Other human BBIs have used the P300 as a trigger for yes-no communication, etc. However, EEG has poor spatial resolution. It's a blurry average of activity from across the cortex, and mostly the cortex's surface at that, since signals from deep brain structures fade by the time they reach the scalp. Subtle patterns, or activity in small deep nuclei, are largely invisible to scalp EEG. If brain A is thinking of something nuanced, a memory, a complex image, an abstract idea, the specific neural code for that is likely entangled with many neurons firing in specific circuits that EEG just can't distinguish. EEG is like a microphone outside a football stadium. You'll hear the roar of the crowd but not the conversations in the stands. To get richer information, we turn to more invasive recording methods. Electrocorticography, ECG, uses electrode grids placed directly on the surface of the brain, usually temporarily, during neurosurgeries, to record activity with far better spatial resolution and bandwidth than EEG. With ECG, one can often detect high-frequency gamma waves localized to specific cortical patches, for example, bursts of gamma in a speech planning area that signify a person is internally rehearsing words. Intracortical microelectrode arrays go even further, piercing into the brain to listen in on individual neurons or small ensembles. The classic Utah array, or the newer Neuralink-style probes, can pick up the spiking of hundreds of neurons in parallel. With these, researchers have decoded incredibly rich signals, for instance, the trajectory of an imagined hand movement, or even an attempted handwritten letter, drawn in the mind's eye. Researchers recently decoded letters that a paralyzed man imagined writing, at about 90 characters per minute, using intracortical electrodes, a testament to how much bandwidth is latent in neural firing patterns. In other work, intracortical recordings from motor cortex have been used to control robotic limbs with fine dexterity, and recordings from auditory cortex or speech areas have been used to synthesize spoken sentences from internal speech. Such capabilities hint that if brain A has an implant tapping into the right area, we might extract far more complex messages than a yes-no, perhaps entire streams of imagined speech or vivid mental images. The trade-off, of course, is invasiveness. Implanting electrodes in a human brain is high risk and done only in extraordinary cases, like clinical trials for paralysis. So for now, the state-of-the-art decoding often happens either in animals or in rare patient volunteers. Non-human primate studies, for example, have shown how a monkey's brain signals can be decoded at high resolution to control avatars or even feed into another brain, previewing what might one day be possible in people. But until implants are safer, wireless, long-lasting, and ethically acceptable for healthy humans, most human-oriented BBIs will stick to methods like EEG or maybe FNIRS, functional near-infrared spectroscopy, or other non-invasive techniques that sacrifice detail for safety. Regardless of how signals are recorded, the next step is decoding. The raw data coming from brain A is just a blizzard of numbers, voltage traces, spike trains, etc. We need to translate that into a meaningful command or message to send. If our goal is extremely simple, say, one bit of information, yes, or no, move, or don't move, the decoding can be correspondingly simple, e.g. threshold detection. Did the EEG amplitude exceed X? Yes or no? In fact, the earliest demos did exactly that. In the Harvard experiment, the system likely just detected when the EEG power at the flicker frequency went above a threshold, and then it triggered the ultrasound pulse. But if we want to transmit something continuous or complex like a hand motion trajectory, or a sequence of letters, or a category of image, we need more sophisticated decoding algorithms. Today, virtually all BKI decoders rely on machine learning. This ranges from relatively simple classifiers, a support vector machine to distinguish left-hand imagination vs. right-hand imagination, EEG patterns, for instance, to hidden Markov models and state space models, to decode sequences of neural states over time, and increasingly to deep learning, neural networks that can learn complex mappings from neural data to intended output. Typically, these models are trained on labeled data. We collect a bunch of examples where brain A does X and record the signals, brain A does Y and record those signals, and so on. Then train the model to predict X versus Y from the signals. Some BBI setups might involve adaptive decoders that update as they get more data, or even use reinforcement learning, essentially trial and error, to improve the accuracy as the brain and computer co-adapt. A key requirement here is speed. Brains operate fast. If it takes your decoder 5 seconds to figure out that the sender thought, rotate clockwise, you've probably missed the moment. Ideally, decoding in a BBI should happen in tens of milliseconds or a couple hundred milliseconds at most, to feel synchronous or interactive. This demands efficient feature extraction. Sometimes algorithms will distill raw signals into key features like frequency power, or the firing rates of top neurons, to reduce dimensionality. And good generalization, the decoder must deal with noise and fluctuations in the brain signals without constantly needing recalibration. Cutting-edge decoders even begin to incorporate predictive models that anticipate changes, or transfer learning that uses previously learned neural patterns to speed up new tasks. But however it's done, by the end of the decoding stage we want a clear message, something like, brain A is thinking yes, with 90% confidence, or, brain A's intended movement vector is, dx, dy. Across the bridge, once we have that message, sending it digitally is the easy part. We've been transmitting bits over networks for decades. Whether via Bluetooth, Wi-Fi, an internet connection, or a wired cable, the BBI channel typically sends a small data packet representing the brain-derived information. In animals sharing a lab, this might be a direct wire or radio link between implant devices. In human experiments, often the data goes through a normal computer over standard networks. There's latency to consider. The UW campus demo sent signals over the internet with only a split-second delay, which is impressive. There's also the prospect of errors or lost packets. Imagine a yes bit flipping to no en route. Encryption and error correction could become important when the stakes are high, a point we'll revisit. In the Nicole's transcontinental rat link, they explicitly tested whether added network noise or delay would break the communication. It didn't, though performance dropped a bit. Brains are somewhat robust to delays. After all, natural neural pathways have variable conduction times, but too much latency can definitely garble a sense of simultaneity. More on this later when we discuss synchrony. On the receiving side, brain B now comes perhaps the hardest part, delivering a stimulus to brain B that the brain will interpret as the intended message. The toolkit for stimulating brains is diverse, but each tool has limits. The most common non-invasive methods are transcranial magnetic stimulation, TMS, and transcranial direct current stimulation, TDCS. TMS, by discharging a strong magnetic coil, can induce electric currents in the cortex to elicit neural activity. It's like a brief electromagnetic poke to a brain region. If you TMS over primary motor cortex, you can trigger a muscle twitch, as in the human BBI demos. You can also use repetitive TMS to modulate cortical excitability, making neurons more or less likely to fire for a short period. TDCS, on the other hand, uses a weak electrical current across the scalp to bias neurons. It won't usually cause a neuron to fire outright, but it can nudge populations into a slightly more excited or inhibited state, potentially influencing things like attention or mood. Both TMS and TDCS are relatively coarse. They affect a broad area and can't target deep structures easily. More recently, researchers have explored focused ultrasound, FUS, and temporally interfering electrical fields as ways to get at deeper brain regions without surgery. Low-intensity focused ultrasound can be directed through the skull to stimulate or modulate tissue at depth. The Harvard experiment's use of FUS on a rat was an early example, and FUS has since been tested in humans to, say, transiently alter mood or reaction times. Temporal interference, developed around 2017, uses two high-frequency electrical signals that intersect in the brain. They are individually too high frequency for neurons to follow, but their interference pattern at the difference frequency can drive neuronal firing in a focal spot. In rodents, temporal interference has stimulated the hippocampus non-invasively, and initial human trials are investigating its potential. Each of these non-invasive methods can carry only so much information. You might be able to deliver a train of TMS pulses at a certain frequency, or oscillating ultrasound at certain modulation rates, but you won't, yet, be painting high-definition patterns on someone's cortex with them. If we allow invasive methods on the receiving side, our options broaden. In animal BBIs, a favorite is intracortical microstimulation, ICMS, sending tiny electrical pulses through an electrode implanted in the brain. This can be surprisingly specific. For example, in monkeys, microstimulating a particular patch of somatosensory cortex might make the monkey feel as if its finger was touched, or microstimulating visual cortex can make an animal see a small phosphine spot of light. Nicolelis's rat experiments used ICMS, zapping the decoder rat's cortex in a pattern that the animal's brain learned to associate with a certain lever or whisker sensation. In principle, ICMS can convey multidimensional analog signals, different electrodes, frequencies, amplitudes, though in practice there's a limit to how much a brain can decipher without training. Beyond electrical pulses, one can imagine using optogenetics in an animal BBI, if the receiver animal's neurons are genetically modified to respond to light, expressing channels that activate or silence the cell when specific light wavelengths hit. Then fiber optic implants or micro-LED arrays could deliver highly precise stimulation to chosen neural subtypes. Optogenetics has achieved single neuron resolution in research settings, which is orders of magnitude beyond what electrodes or TMS can do. This could, in theory, allow a language of brain communication encoded in the firing of specific ensembles of neurons, but it requires invasive genetic tinkering and hardware, so it's not remotely applicable to humans right now. Still, these emerging tools hint at where we might be headed, technologies that can write to the brain as flexibly as we now read from it. Regardless of method, the central challenge on the receiver side is one of encoding, translating the decoded message into a pattern of stimuli that brain B will correctly interpret. For something like a simple motor command, the encoding can be straightforward. Stimulate the motor cortex region that controls, say, the right index finger, and that finger will twitch. Mission accomplished. Indeed, BBIs so far often choose motor actions as the conveyed information because the code for basic movements is relatively well understood. A certain area fires, a certain muscle moves. But what if the information is abstract, like yes versus no, or the image of a cat, or the concept of an apple? We don't have neat cortical buttons for those. One strategy has been to convert such information back into a sensory form for the receiver. For example, if the sender's intention is yes or no, we can encode that as two different stimuli delivered to the receiver's brain. In one study, the choice to rotate a Tetris piece or not, essentially a yes-no bit, was encoded by two different TMS patterns delivered to the occipital cortex of the receiver. The TMS would induce a visual disturbance, perhaps a flash or a pattern, that the receiver learned to associate with rotate vs don't rotate. Over repeated trials, the receiver got better at interpreting these incoming neural cues, essentially learning a tiny vocabulary of two symbols delivered via brain stimulation. It's slow and clumsy, more like learning to read flag semaphore than hearing someone speak, but it does work. Another team created a human BBI where one person's brain signaled yes or no, and the other received that signal as a TMS-evoked phosphine in either the left or right visual field, indicating option A or B. The receiver had to interpret this flash location to guess the answer to a question. Accuracy was modestly above chance, but definitely better than random, proof that even very limited stimulus patterns can convey meaningful info when humans train on them. For richer information, one intriguing approach is to mimic what's been learned in sensory prosthetics. Consider how a cochlear implant gives hearing to the deaf by electrically stimulating the auditory nerve according to sound frequencies, or how visual prosthesis research is attempting to create artificial vision by stimulating arrays implanted in the visual cortex. If one brain could supply the signals that normally come from an ear or an eye, then in theory the other brain could feel or see what the first brain is experiencing. In a futuristic scenario, if Alice is looking at an image and we capture the essence of what she sees, we could stimulate Bob's visual cortex in a patterned way to make Bob perceive a rough version of that image. The technology to do this is still in early stages. Even the best current visual cortical prostheses produce only phosphons, like seeing a sparse dot matrix. But one can imagine that as high-density neural interfaces advance, a BBI could leverage them. Sender imagines an image. The signal is decoded. The pattern is re-encoded and delivered to the receiver's visual cortex. The receiver sees a flash, not of light, but of thought, as one commentary put it. It sounds fantastical, but it's a logical extension of where both BCIs and sensory prosthetics are headed. At present, almost all working BBIs keep things extremely simple, often just a single bit or a few bits of information, like a yes, no or left-right decision. And yet, even these sparse links have yielded striking results. Take the BrainNet experiment at University of Washington in 2019 that we touched on earlier, a triad of people collaboratively playing a Tetris-like game via a BBI network. Two people, the senders, could see the game and decide whether the block on screen should be rotated. They indicated their decisions by focusing their eyes on a yes or no flashing LED, 17 Hz vs 15 Hz, which their EEG caps could detect via the distinct frequency brain response. These yes-no bits from the two senders were then sent to the third person, the receiver, as magnetic pulses to occipital cortex, essentially giving the receiver two flickers that, once trained, they would interpret as votes from sender A and sender B. The receiver could not see the game, so they relied solely on these brain-delivered votes to decide whether to rotate the piece. Over many trials, the trio developed a rhythm. The receiver learned to trust the more reliable sender. Each sender had different accuracy, and the team's overall performance at the game was significantly above chance. This was a primitive form of distributed decision-making via BBI. No words or glances were exchanged. The group coordinated purely through neural signals. In effect, they formed a three-brain system to play a game. As the researchers pointed out, this is the first demonstration of more than two human brains linked in direct communication. The game itself was simple and the messages, only yes-no, but it revealed a profound principle. You can share mental state directly to solve problems together, albeit in a rudimentary way. These experiments underscore a big point: cognition can be distributed. We humans already distribute cognition all the time through natural means. Think of a pair of pilots jointly flying a plane, each monitoring some instruments and cross-talking, or a band improvising music where each member intuitively meshes with the others. In those cases, communication is happening through speech, gestures, and mutual perception. BBI's promise to take that a step further, potentially linking brains in ways that bypass the ambiguities of language or the slowness of deliberate communication. When multiple brains share even a little information directly, they can, under the right conditions, perform as a unit that's more than the sum of its parts. The rats achieved better discrimination as a network than alone. The BrainNet humans made joint decisions, and multiperson EEG studies, without direct brain links, just combined signals, have shown that pooling brain data from several people can improve detection of faint signals or vigilance in tasks. It's reminiscent of ensemble methods in machine learning, where combining multiple models, or opinions, yields better accuracy than any one model alone. Each brain has its noise and biases, but if you integrate several brains, the noise can average out and the strengths reinforce each other. A BBI is a literal instantiation of a hive mind on a small scale, not the sci-fi hive mind of total mind meld, but a pragmatic one where each brain contributes to a group computation. Naturally, this raises the question, how far can this go? We've gone from one bit, move-tailed not, to a few bits, yes-no to play a game. Could we scale to transmitting thoughts, memories, skills? What are the fundamental limits? It helps to break the challenge down into a few key dimensions: bandwidth, representation, timing, and cognitive state. Bandwidth. In information theory terms, bandwidth is the rate at which data can be transmitted. Our natural human communication bandwidth varies by mode. Speech carries maybe 50 to 100 bits per second of information, since we speak perhaps 150 words per minute, and a word is a few bits if optimally encoded. Typing or texting is slower, maybe a few tens of bits per second. Vision is enormously high bandwidth. The human retina streams on the order of megabits per second to the brain. One estimate pegs the optic nerve around 10 million bits per second in capacity, comparable to an old Ethernet cable, as researchers at University of Pennsylvania quipped. But current BBIs are nowhere near that. We're lucky to get a few bits per second through a direct brain link reliably. Nicolalys's rats, the UW BrainNet, the OLA messenger, all of these transmitted on the order of 1 bit in a few seconds, or maybe 5 to 10 bits per minute. Why so low? Partly technical limitations. Non-invasive recordings only pick up very coarse signals, and non-invasive stimulation can't deliver much complexity. But partly it's the neural code challenge. Brains don't communicate in ASCII or some neat binary protocol. Neural signals are noisy and deeply embedded in context. Extracting a clean high bit rate message like, "Here is a detailed image I'm thinking of," encoded in 100,000 bits, is vastly harder than intercepting a keyboard's output. And on the flip side, injecting 100,000 bits into someone's brain in a second would almost certainly overload them or just come through as meaningless noise. The brain isn't a blank hard drive waiting to be written, it's a living system with its own rhythms and content. Thus, early BBIs have wisely stayed in the shallow end of the bandwidth pool. That said, we can expect bandwidth to improve as technology and neuroscience advance. On the sending side, as mentioned, high-density implants can already record from hundreds or thousands of neurons simultaneously. With advanced signal processing and AI, we can potentially decode a large amount of information from such neural ensembles. Imagine brain A sending not just a yes-no, but a whole vector of intended movement or a sequence of phonemes for a word. Recent BCI researchers, for instance, decoded roughly 15 words per minute of imagined speech from ECOG in a clinical trial that's on the order of 40 bits sec if error-free, already approaching conversational pace. If such a stream were piped into another brain's speech areas via stimulation, we might get a crude direct brain-to-brain dialogue. It's still speculative, but not fundamentally impossible. On the receiver side, current methods are a bottleneck. TMS can only induce maybe up to 20 pulses per second, beyond that it becomes either unsafe or just a blur. TDCS can't convey any fast signals at all. It's like setting a knob and leaving it for minutes. Focused ultrasound and temporal interference might deliver at higher frequencies or target more channels independently, but they are in early stages. For true high bandwidth, we might need invasive stimulation, arrays of electrodes or optogenetic lights that can stimulate dozens or hundreds of sites in the brain simultaneously with millisecond precision. That is exactly what some vision prostheses are attempting. For example, one device implants an array of 60+ electrodes in visual cortex to create rudimentary patterned vision for the blind. A future BBI might employ an implant in the receiver with, say, 1,000 stimulation channels, essentially writing 1,000 bits in parallel into the cortex at once. If each channel could be modulated at, say, 200 Hz, that's 200,000 bits per second, 200 kbps, theoretical throughput, not saying we could interpret it all, but physically that's in the realm of early internet modems. Brains are enormously parallel, so in principle the bandwidth ceiling is very high if we figure out how to harness it safely. But even if the tech allows it, there's a deeper issue: shared understanding. Representation, shared code. Suppose brain A and brain B have a megabit channel between them. How do we ensure that the patterns sent are meaningful to the receiver? When we humans communicate with language, we rely on a vast shared context, vocabulary, grammar, worldly experience. Brains don't automatically share a common, neural language. The pattern of neural firing that corresponds to red apple in my brain is certainly not identical to that in yours, though there might be some common anatomical pathways involved. If I somehow send the exact neural firing pattern of my red apple concept to your brain, there's no guarantee your brain will interpret it as apple. It might interpret it as something entirely different, or just nonsense, because it doesn't have the same tuning or associations that mine does. This is a profound problem of neural code compatibility. Communication, whether neural or verbal, presupposes a common code. With BBIs, we have to either establish a common code or brute force our way by training the brains to understand each other through feedback. In practice, BBI researchers have started simple. they transmit signals that have an obvious inherent meaning, like firing in motor cortex that makes a rat press a lever. The receiving rat's motor cortex is wired similarly, so stimulating it in an analogous way produces the lever press action, which is the right interpretation. Or they use arbitrary signals that the receiver learns to interpret during the experiment, effectively creating a mini shared code by training both brains. In the human yes/no cases, the receiver's brain doesn't intrinsically know what a TMS pulse means. The person has to learn, okay, a flash on the left means yes, on the right means no, for that specific pairing and that specific task. Over repeated trials, both the stimulus delivery might be tweaked and the receiver's brain adapts, a process we can call co-training. Essentially, the two brains and the computer between them gradually develop a shared language of signals. It's analogous to how two people might develop a private sign language if stranded on an island, initially crude pointing, but over time a richer set of signals with agreed meanings. In a BBI, the agreement is partly forged at the neural level. The receiver's brain pathways adjust to make sense of the incoming stimulation, and the senders, and decoders, might adjust to make their outputs more interpretable. This dynamic was observed in the BrainNet experiment, where the receiver improved at discerning which sender was more trustworthy by internally calibrating to their signal quality. We can imagine future BBI systems having an explicit calibration phase, much like two radios tuning to the same frequency and protocol, where the brains engage in back and forth training until a reliable set of neural signal meanings is established. A more radical approach to the representation problem is to try to create a universal neural code, or at least a bridge between different brains' codes. Some theorists have speculated about mapping individual brains' neural activity into a common high-dimensional space, akin to how AI models use embeddings. For example, in natural language processing, different words or even different languages can be mapped into a shared vector space. Think of how dog in English and in Japanese would occupy analogous points in a concept embedding space if the model is trained on translations. One could imagine an analogous brain embedding space, where one brain's pattern for apple and another brain's pattern for apple both map to the same abstract representation. Then the BBI system could translate from brain A's idiosyncratic neural code to the shared code, then from the shared code into brain B's neural patterns. In essence, the computer in the middle would act as a real-time interpreter between two foreign neural languages. This is a very ambitious goal, and we're far from achieving it, but it's conceptually akin to how brain-machine interfaces might translate neural signals into machine instructions and back out into neural stimulation. Perhaps machine learning could derive such a shared latent space by training on lots of data from many brains, a kind of Google Translate for neural data. If successful, it would mean any two individuals could speak to each other's brains once their signals are mapped to the common representation. Early research in this vein might involve, say, training decoders that work across multiple people. Some progress has been made in having one AI model decode neural data from many individuals by finding common features, though the brain-to-brain use of that is still theoretical. A simpler tactic available now is what we might call sensory common ground. Instead of directly inserting abstract info into brain B, convert it into a form brain B naturally understands through its own senses. For instance, if I want to transmit a complex message to you, I could use a BBI to stimulate your visual cortex with a pattern that literally spells out the message in flashes of light or plays a sound in your auditory cortex. But at that point, one might argue we're just using a very convoluted way to achieve what a pair of augmented reality glasses or earbuds could do. Why stimulate the brain to hear a tone encoding Morse code when I could just play a tone to your ear? Indeed, some researchers talk about brain-to-brain to sensory hybrids, where the brain signal from A gets turned into a sensory cue for B, leveraging B's intact sensory system. That's arguably not a pure BBI, since B is using their normal sensory pathways, but it might be practically easier for many applications. For example, suppose a pilot's brain detects a threat and we want another pilot to instantly be aware. One could flash a light to the second pilot. That's a form of mediated communication that still achieves nearly instant sharing of a detected event, just not via direct cortex-to-cortex injection. The purest vision of BBI, though, strives for direct neural exchange without translating out to overt stimuli, because truly silent, covert communication between brains, especially if the people are far apart or if one can't communicate normally, is a unique capability. Still, the line can blur. If the end goal is high bandwidth and reliability, some hybrid of direct neural links and traditional sensory channels might be the most practical in near term. Timing and synchrony. Another critical factor in BBIs is timing. Our brains are not static encoders of information, they are time-sensitive, oscillatory, and state-dependent. If I stimulate your brain with the exact same pattern but at two different times, say once when you're attentive and expecting it, and once when you're distracted or in a different brain rhythm, the outcomes can differ. Neurons respond differently depending on their current excitability and what other processes are ongoing. Thus, a BBI signal might succeed or fail to integrate purely because of timing mismatches. For instance, if brain B is busy processing something else or is in the wrong phase of an alpha oscillation when the input comes, the signal might be ignored or misinterpreted. This has led to an idea called cognitive phase locking. Try to synchronize the stimulation to the natural rhythms of the receiver's brain. If the receiver is in a theta rhythm, perhaps deliver pulses aligned to a certain phase of that rhythm where cortical excitability is highest. Some experiments in brain stimulation have found that TMS can have very different effects depending on whether it's applied at peaks or troughs of ongoing oscillations. So a closed-loop BBI might monitor the receiver's EEG in real time and only inject the message at the optimal moment, like timing your interjection in a conversation to when the other person is listening. Additionally, receivers might need to be put in an expectant state to receive info. Just as you can't understand speech if you're not paying attention, a brain might tune out incoming artificial stimuli unless it's primed to pay attention. A receiver could, for example, get a cue, even a subtle subconscious one, that information incoming, ready yourself. Or the system can itself detect whether the receiver's brain is in an attentive state and hold off stimulation until it is. This begins to make the BBI a closed-loop system in a larger sense, not just a one-way send, but a continual monitoring and adjustment, where brain B's receptivity is tracked and brain A's output might even be adjusted on the fly to maximize mutual understanding. In some animal BBIs, the loop was closed by reward, e.g., if the decoder rat failed, the encoder rat got no reward and altered its behavior, as we saw. In human BBIs, we might incorporate feedback like an error signal if the message wasn't understood, prompting the sender, or the sender's assisting AI, to try again differently, and the receiver's brain to recalibrate. So, expanding bandwidth, aligning representational codes, synchronizing timing, and managing brain state, these are the frontiers being tackled now. Each draws on different fields: signal processing, machine learning, cognitive neuroscience, even linguistics and communication theory. It's a grand interdisciplinary puzzle. But beyond the technical challenges, BBIs prompt us to reimagine what an interface can be. We're not just talking about controlling a cursor or feeling a haptic buzz, we're talking about interfacing two minds. This is a fundamentally new category of connection, and it naturally leads to philosophical questions as much as engineering ones. What's the smallest unit of thought or experience that can be sent from one brain to another? Is it a sensation, like red or warm? Is it an intention, like press the button now? Could it be a more complex state, like an emotion? Could I make you feel a bit of what I'm feeling, or a memory? Early BBIs are nowhere near transmitting a memory or a mood, but as we push the limits, we have to ask what in principle could be shared. Are we heading toward a future where knowledge itself can be transferred brain to brain, like downloading information? Or will it be more like sharing influence, nudges and partial information that, combined with the receiver's own brain, lead to a converged thought? Even these questions were once purely speculative, the domain of sci-fi novels where people merge minds, or hackers jack into each other's heads. Now they are becoming concrete research questions. Engineers and ethicists are pondering them side by side. From a historical perspective, human communication has been a story of extending our thoughts farther and faster. Gestures let ideas jump between people within sight. Language let complex ideas transmit symbolically. Writing preserved ideas across time and space. Telegraphs and phones bridged distance instantaneously. The internet scaled that globally. Each step has increased the abstraction and reach of our communications. Brain-to-brain interfaces could represent the next step, not replacing language, but underpinning it with a new layer, potentially an unspoken, immediate layer. It could be akin to sharing raw experience or intention beneath the veneer of words. Some have imagined that if such interfaces matured, humans might develop a kind of meta-language or directly share mental models, altering how collective thinking happens. Importantly, none of this implies loss of individuality or a hive mind in the terrifying sci-fi sense. In fact, a well-designed BBI might enhance individuality by allowing people to share what they choose at a deeper level, leading to greater understanding. Just as reading a great author's book can influence your mind profoundly, yet you remain you, experiencing a trace of someone else's thought via BBI might broaden your perspective without erasing it. BBIs, ideally, would be used as augmentations to communication and cognition, not as replacements for our inner voice. We are, as of now, firmly in control of what we choose to communicate or not, and any future BBI would need to preserve agency and consent as sacrosanct. More on the ethics soon. Before diving into the ethics and far futures, let's stay a bit longer with the emerging concept of multi-brain architectures. If 2 brains can be linked, why not 3, or 10? The BrainNet experiment gave us a glimpse of a 3-brain network solving a task. It revealed phenomena like trust formation, the receiver learned which sender was usually correct, effectively weighting that input more, a simple form of network weighting, or who's the expert logic that emerged organically. Scale that up to larger groups and more complex information, and you start to envision networks of brains working in concert, a biological parallel to cloud computing, but with minds. This might sound radical, but it parallels things we already do. Consider a surgical team performing an operation. They operate with exquisite coordination, often wordlessly, anticipating each other's moves, aligning attention on the patient. Communication is happening through glances, via the shared context of training, via the patient's vital signs, etc. Now imagine that in addition to those channels, the team has a direct BBI link sharing, say, an integrated sense of the patient's state or each other's confidence levels. It could reduce miscommunication further and synchronize action almost like a single organism. Or think of a special forces military unit in a high-stakes mission, where every member is in sync. Today they use hand signals, radio calls, and intuition. A future BBI network might allow them to share key bits of tactical intent silently and instantaneously, effectively giving them a collective situational awareness that's a sum of all individual perspectives. Indeed, DARPA has funded preliminary research into shared perception via neural means, aiming to enhance team performance. In less adrenaline-filled scenarios, consider a multilingual team trying to collaborate. Person A has deep knowledge of Chinese, Person B of Russian. If both could be linked such that each one's language comprehension could be partially shared, the group might solve translation problems in real time by pooling their linguistic brains, a sort of neural polyglot team where each member contributes their strongest language to a common understanding. These are speculative examples, but they map onto a real principle. Joint attention and shared context improve group outcomes, and BBIs could amplify joint attention to the neural level. If we think of a network of brains, we can also consider network topologies. Is it one central brain broadcasting to others, a hub and spoke? That might happen if, say, one expert brain provides guidance to multiple novices, analogous to a single teacher's brain feeding into many students as a central node. Or do we have a fully connected mesh where everyone's brain exchanges with everyone's? That could be overwhelming, but maybe small cliques could mesh on specific subtasks. Or hierarchical, where maybe lower-tier processors, brains doing part of a computation, feed intermediate, integrator, brains, and so on up to a leader who makes a final decision. Each architecture might suit different scenarios. A brainstorming creative group might prefer a more egalitarian mesh, everyone throwing in neural ideas, whereas a squad of fighter pilots might prefer a hierarchical system with a commander integrating the other's threat signals and making quick decisions. These structures bring to mind how artificial neural networks are organized. Interestingly, we could end up designing brain networks in ways that mirror AI networks, with layers or modules specialized for vision, language, etc., except each node is an actual human mind contributing its forte. One person might be especially good at spatial navigation, another at mathematical reasoning. A BBI network could route the relevant parts of a problem to the person best equipped to handle them, then share the result with the group. In computer science, this is akin to distributed computing or ensemble methods. In a human BBI context, it means enhancing group intelligence by capitalizing on each member's strengths in real time. With these possibilities come profound ethical and social questions. If a thought or decision is truly co-authored by multiple brains, who is responsible for it? Imagine a future scenario where a brain network of several people working together comes up with a plan that turns out to be disastrous. Each individual alone might not have conceived the plan. It emerged from their interaction. Do we blame the group as a whole? Do we assign percentages of blame to each person's contribution? Our current frameworks of accountability assume individual agency, but tightly coupled brain networks could muddy those waters. Likewise, if a group of people via BBI share an experience or memory, do they all own that memory? Could one person's recollection be edited or erased by another's intervention? Far-fetched perhaps, but if you literally share a memory engram, could it even be located in whose brain originally? These edge scenarios raise questions of mental privacy and autonomy on a level we've not confronted before. Already, neuroethicists talk about cognitive liberty, the right to freedom of one's mind, and suggest that practices like BBI would need clear consent protocols and boundaries to ensure no one's sense of self is violated. Encouragingly, initial BBI studies have been very limited and done with full consent in lab settings, but as the tech evolves, misuse could be conceivable, e.g., could someone be coerced to receive brain stimulation carrying information they don't want? Another issue is the balance between unity and diversity. Sharing information at the speed of thought could lead to over-synchronization. In a group, if everyone's brain state starts mirroring each other too closely, you might get the neural equivalent of groupthink, a loss of independent thought and creativity. Small differences in perspective are often what lead to creative solutions or error correction in teams. If a BBI network smoothed those out too much, a group might become too coherent, marching together off a cliff that a lone dissenter could have avoided. Designers of multi-brain systems might need to deliberately introduce a bit of latency or noise, or limit what is shared, to preserve individual divergence where needed. Perhaps users will have dial settings. You could turn up the sharing for tasks requiring tight cooperation, and turn it down when you need independent thought. This also touches on exit rights. One should be able to disconnect from the network at will. Fluid entry and exit without cognitive residue was phrased in one research vision. Cognitive residue meaning, you don't want to leave a group mind and find that you can't distinguish which ideas were yours and which came from others, or worse, that you can't stop others' voices in your head. That would be a nightmare scenario, so any practical BBI would require robust safeguards that keep contributions and identities well managed. Maybe the experiences shared would always be tagged in some conscious or subconscious way as other originated, so you maintain a sense of self. Technically, scaling BBIs to many nodes compounds the engineering difficulties. Sifting signals from multiple brains, synchronizing stimulation across several individuals, Avoiding crosstalk and interference, it's a monumental challenge. We might need new forms of neural multiplexing, ways to encode different streams of information for different recipients without jamming the circuits. It's analogous to having many people talk on one radio frequency. You'd need either time sharing, frequency sharing, coding schemes. Similarly, many brains could saturate a channel if not properly coordinated. There's also the sheer data problem. A direct brain link that's high bandwidth might produce firehose streams of data. Combining them from multiple people could overwhelm current processing abilities. Advances in real-time neural data compression and filtering will be key. We might only transmit changes or highlights rather than raw signals, for instance. And consider the practical logistics. If we have, say, a 5-person BBI for a task, each person might need an implant or wearable with wireless communication. The system must ensure that each person's device knows which incoming signals belong to which sender, etc. Secure pairing and group network protocols will be needed to prevent mix-ups. Imagine the confusion or danger if brain A's intention accidentally stimulates brain C instead of B. This veers into the domain of cybersecurity, neurosecurity, really. Indeed, neural security may become a critical field if BBIs become widespread. In a connected BBI, you wouldn't want an external actor hacking in and eavesdropping on the group's shared brain signals, or worse, altering them, the equivalent of intercepting and changing messages in a network. Encryption of brain data might be necessary, along with authentication protocols. How does your brain verify that the signal it's receiving is truly from your teammate's brain and not some malicious spoofer? It's a bit surreal to think about, but if brain-to-brain messages are flying around, they could be subject to the same vulnerabilities as any digital communication. And the consequences of a breach could be far more personal. This is not someone reading your email, it's potentially someone gleaning information from your neural patterns or injecting false thoughts. We will likely need cortical firewalls, perhaps devices that gate what kind of stimuli can enter, and alert a user if something seems off or unverified. Just as today we worry about computer viruses, tomorrow we might worry, in the worst dystopia, about mind viruses, not metaphorical ideas, but actual malicious BBI signals. This all sounds very Black Mirror, and it is, which is why researchers are already advocating ethical frameworks and technical safeguards now, at the early stages, so that as capabilities grow, safety and privacy aren't an afterthought. Another mind-bending possibility is the idea of recording and archiving mental states. If a BCI can record a memory pattern from brain A and a BBI can inject it into brain B, could we start to treat certain memories or skills almost like files? Could you save a mental state and replay it later, either into yourself or someone else? Neuroscience is far from being able to do that for complex episodic memories. We can't just copy-paste a memory of your 10th birthday into someone else's head. But simpler things, like the neural activation of a learned skill, might be partially transferable. There was a study some years back that claimed to use a form of non-invasive BBI to transmit a simple learning, like a particular motor response bias, from one person to another. It was basically a conditioning paradigm. One person's brain signals when they got something right were used to stimulate another person during the task, subtly biasing them. The effect was minor, but it raised eyebrows that knowledge, however trivial, might be transferable. One could imagine training data being distilled into a neural pattern, say a pilot's brain recording when performing a perfect landing, and that pattern used to stimulate a trainee's brain to imprint the ideal action. That starts to sound like The Matrix. I know Kung Fu, after a quick download, which is wildly beyond current science. But in smaller ways, like transferring mental states, it might be possible sooner. If one person is very calm under pressure, a BBI might transmit signals corresponding to that calm state into another person to help them through an anxiety akin to one brain lending emotional support by directly imparting its state of tranquility. In fact, researchers have speculated about empathetic BBIs for couples, where one partner can help regulate the other's emotions in real time by sharing a bit of their neural patterns when they are calm or happy. It gives new meaning to the idea of feeling someone's pain or sharing someone's joy. We'd have an actual electrical analog of empathy. This also touches on what might become cognitive prosthetics from other brains. Say an elderly person beginning to lose memory could be linked occasionally with their younger family member's brain to help stimulate certain circuits and keep them active. Or in therapy, a patient with depression might benefit from periodically experiencing small doses of a friend's non-depressed brain activity to nudge their neural networks towards a healthier pattern. That's speculative and would need to be done extremely carefully to avoid adverse effects. But conceptually it's like starting someone's car battery with another's. For all these potentials, we must remember that the brain is not a hard drive. You can't just write data arbitrarily without the brain's own dynamics interpreting, filtering, or even rejecting it. That's why co-training and adaptation are so important. A BBI is as much about two brains learning to dance together as it is about raw data transfer. Each brain will have to maintain its own integrity and yet find a rhythm with the other. Early BBIs are more like two dancers clumsily tied together. Future ones might be as fluid as a well-practiced tango where each partner responds to the slightest cue from the other. In those aspirational visions, a person linked to another might have the experience of a thought arising that is partly theirs, partly not truly a shared thought. Some philosophers call this concept we-intentionality, an intention or thought that belongs to a we instead of an I. In the context of a BBI, it could be literal. Imagine a group brainstorming via BBI. Ideas might bubble up that no single person feels they came up with alone. It emerged from the group's interwoven neural activity. This challenges our notions of creativity and ownership, but it also excites them. Many of humanity's great achievements are the product of collective thinking over time. Perhaps BBIs could accelerate that by letting minds truly merge their perspectives in the moment. Stepping back, it's important to emphasize that as of 2025, BBIs are still in their infancy. We have a handful of proof-of-concept experiments, mostly transmitting very simple information with limited reliability. But the trajectory extrapolating from BCI advances and from the rapid progress in AI for decoding brain activity suggests that the coming decades could see leaps from those one-bit twitches to far richer exchanges. Just in the last few years, AI models have decoded speech from brain recordings and even reconstructed rough images from fMRI scans using generative networks. It's not implausible that a decade from now, we might see a human BBI attempt to send, say, a primitive visual image, like a letter or a simple shape, from one person's mind to another's. Or perhaps a mood, maybe one person's EEG profile of a meditative state could be delivered to another in such a way that it induces a similar state. Each step will be met with scrutiny for safety and ethics, but small pilot studies are likely. On the horizon beyond, one can imagine consumer applications if BBIs become safe and unobtrusive. People might opt to link with their partner for a few minutes each day for a deep wordless check-in of emotions. Creative teams might use a shared network mode during intensive design sessions to rapidly exchange half-formed ideas as a collective mental sketchpad. Teachers might do a neural upload of foundational concepts to students to augment traditional teaching, though true knowledge upload, as in sci-fi, is probably much farther off, if ever feasible. Entertainment and VR could be transformed. Multiplayer games might involve literal mind meld teamwork or competition where you try to influence each other's decisions via neural moves. An entire genre of neuronetwork experiences could arise, the same way the internet spawned social media. Perhaps a brainnet could spawn new forms of collective art or storytelling. The upside potential is enormous: increased empathy, faster innovation, assistance for those who can't communicate normally, new artistic media, and enhanced group productivity, to name a few. But along with this come the downsides we've been careful to consider: privacy risks, security threats, identity disturbances, and social implications. Would such technology widen inequality if only some have access? Would it create new forms of exclusion or pressure, e.g., companies expecting employees to join a work-brain network for efficiency? The ethical frameworks will need to evolve in tandem. Likely, early adopters will be medical, helping the locked-in communicate, or aiding rehabilitation by linking healthy and impaired brains. Some experiments in animals have linked a healthy rat's brain to a stroke-affected rat's brain to aid recovery of function. This medical focus can help society build familiarity and trust in a context with clear benefits. As it moves into broader use, transparency and consent will be paramount. People will demand, rightfully, the ability to control exactly what is shared and when. That might mean user-friendly interfaces, ironically, likely computer interfaces, that manage your neural privacy. Perhaps you wear a device that literally has a privacy mode, LED that assures you no signals are leaving or entering your brain network unless you allow. One can even imagine a future ethical norm. Just as today it's abhorrent to secretly drug someone, tomorrow it would be abhorrent to connect to someone's neural device without permission or to send them unsolicited neural stimuli. Neurocrime might be a term. It sounds wild, but illegal brain hacking could be a concern our grandchildren's generation debates legislation for. Let's not end on the dark notes, though. Throughout history, every time we've developed a new way to connect people, be it language, writing, telephone, internet, it has unlocked incredible progress alongside new challenges. Brain-to-brain interfaces would be among the most intimate connections imaginable. Used wisely, they could deepen human collaboration and understanding beyond language. Imagine truly sharing in someone's inner world, not invading it, but walking alongside their thoughts. It could foster empathy at a level we've never had. Prejudices might melt away when you literally feel a glimmer of someone else's perspective. Teamwork in science, art, and problem-solving could reach heights unachievable by isolated minds. Each individual mind is wondrously powerful, but also limited by its singular experience. Networked minds could transcend some of those limits, forming a collective intelligence that tackles problems like climate change or interstellar navigation with combined insight. Crucially, each mind in the network also serves as a check and balance for the others, keeping the group grounded and diversified. In the best case, BBIs could augment our individuality and our shared humanity, a paradox that might just be possible. Each mind, when linked, doesn't lose its uniqueness, rather, it can see itself in contrast and harmony with others more clearly. A metaphor: think of musical instruments in an ensemble. A violin doesn't cease to be a violin when playing in a string quartet, it retains its timbre, but the music created together is richer than any solo. Similarly, BBIs could allow human minds to create a mental music together, a cognitive symphony, while each brain still contributes its unique voice. What began with a sleeping rat's tail twitching at a human's thought has brought us to the brink of a new mode of existence, one where experience itself can be shared directly, mind to mind. The interface is no longer just between human and machine, or brain and computer, it is between consciousnesses. We stand at the dawn of an era where communication might transcend words and signals to become a merging of states, a true meeting of minds. Whether this future unfolds slowly and cautiously or rushes in boldly is up to us. The technologies will come, in one form or another, of that. The steady progress of BCI research and the tantalizing early BBI results are strong indicators. The architectures, the specific ways we link and safeguard our minds, will evolve, undoubtedly influenced by ongoing dialogue between scientists, ethicists, policymakers, and the public. The fundamental human questions remain as they always have: what do we choose to do with our tools, and who do we become in the process? As we peer through the newly opened door of brain-to-brain communication, we should remember that every interface we build is ultimately in service of our collective values and desires. BBIs will challenge us to define those values clearly, to decide what we most want to share, and what we must protect, in the frontier of our minds. The door is open, it's up to us to walk through with both curiosity and care, and to build, with intention, the kind of connected future we truly want. Sources: Harvard researchers led by Sung-Shik Yo demonstrated the first human-to-animal BBI, using EEG-triggered focused ultrasound to non-invasively stimulate a rat's brain, causing a tail movement about 94% of the time. This showed simple intentional signals can directly activate another brain's motor output. Nicolalis's lab linked rats' brains, transmitting sensoromotor information via intracortical microstimulation. An encoder rat's cortical activity for a lever press task was sent to a decoder rat, which responded correctly 70% of the time without its own cue. If the decoder erred, the encoder adjusted its signals, indicating two-way cooperative communication emerged. In 2015, Nicole Lees et al. Introduced the concept of a brain-it, networking multiple animal brains. In one scientific report study, groups of rats and monkeys literally merged their brain activity to perform tasks. For example, 3 monkeys jointly controlled a virtual arm in 3D, each monkey contributing to certain dimensions of movement, and ensembles of 4 rats performed pattern recognition and even weather prediction computations better collectively than individually. These brain-its illustrated the potential of distributed computing across brains. Rio and Stocco, University of Washington, achieved the first human-to-human BBI, 2013. The sender's EEG-detected motor imagery, thinking about firing a cannon in a game, was transmitted online to a TMS coil on the receiver's motor cortex, causing an involuntary finger twitch to press the fire button. The sender experienced the eerie excitement of seeing his thought trigger another's action, while the receiver likened the feeling to a reflex or tic. This non-invasive brain-to-brain link was later rigorously reported as the first direct human BBI. Grau et al., 2014, demonstrated conscious brain-to-brain communication in humans across 5,000 miles. Binary-coded words, "Ola" and "Ciao" were sent from a person in India via EEG to a person in France, whose visual cortex was stimulated with TMS to induce perceivable light flashes that encoded the message. This showed that simple semantic information, yes/no signals forming words, can be transmitted directly between brains through computer mediation, without using peripheral nerves or muscles. The BrainNet experiment, Science Reports 2019, linked 3 human subjects in a direct brain-to-brain network to collaborate on a Tetris-like task. 2 senders conveyed, rotate, vs, don't rotate, decisions via EEG signals, distinguishable by focusing on different flashing LEDs, which were delivered as TMS pulses to a receiver's brain. The receiver, unable to see the game, integrated these brain inputs and decided on the move. Over trials, the triad achieved about 81% accuracy and the receiver learned to trust the more reliable sender's input. This was the first multi-person, non-invasive BBI for collaborative problem-solving, highlighting that neural information can be shared among multiple minds to perform a task. BBI bandwidth remains very low compared to natural communication. Human speech typically conveys on the order of 50 bits per second, and the human retina streams visual data at an estimated 10 to the power of 7 bits s, roughly 10 megabits per second, comparable to an Ethernet link. By contrast, present BBIs only transmit a few bits per second at best, often binary signals. The gap is due to noise and limitations in current recording stimulation methods. Brains don't yield or accept high-fidelity data easily. Expanding this bandwidth is an ongoing challenge. Researchers envision richer BBI in the future by leveraging advances in neural interfaces. For instance, high-density cortical implants could stimulate patterns on a visual cortex analogous to a low-res image, allowing one person's imagined image to be seen by another via induced phosphons. While structured visual or abstract stimuli remain aspirational, such concepts guide long-term research into multi-channel stimulation for complex percepts. Ensuring the receiver interprets the signal as intended, shared representation, is a fundamental hurdle. Some experiments use co-training. The sender and receiver engage in repeated trials, gradually aligning their neural responses and interpretations through feedback. Over time, a stimulation pattern that was initially confusing to brain B can come to reliably represent a specific concept, akin to two people developing a shared code. Researchers have speculated about training brains to map their activity into a common latent space, analogous to how AI models use shared embedding spaces. In theory, this could allow one brain's encoded concept to be correctly decoded by another brain even without direct trial-by-trial calibration, by translating through a universal neural code. As BBIs scale, neurosecurity becomes critical. Any brain-to-brain communication channel could be vulnerable to interception or manipulation if not secured. Researchers note that privacy in the BBI era will require encrypting neural signals and authenticating partners. Just as we protect data packets on the internet, signals between brains must be safeguarded against spoofing or eavesdropping. The notion of gating your cortical ports is introduced. Users might need personal neural firewalls to ensure only trusted, consented signals enter their brain. This is not merely speculative. As early as 2014, experts warned that brain-computer interfaces could become targets for hacking, and the advent of BBIs amplifies those concerns. Robust permission protocols, signal integrity checks, and fail-safes, like an emergency, disconnect, or shut off, will be integral to any real-world BBI system.